what we have seen in electrical circuits, because I gave it to you in an email, that P is equal to I times V. That seems meaningless to us, to you, because we don't really have a concept, a conceptual picture of what I and V and P are, right? So I want to show you some things, right? First of all, is that briefly in the opening notes, I told you that voltage or potential difference was a characteristic that led to potential energy, right? It's not potential energy in its own sense, it is energy per unit charge, right? So voltage, V, is work divided by charge, which is Q. Charge can be represented as capital Q or lowercase q. Generally, if we're using lowercase q, we're probably talking about electrons. And more importantly, we're talking about charge that is moving, right? Which makes sense because what moves in an electrical circuit?
Electrons.
Electrons through the wires. So lowercase q in this particular case is representing an electron moving through the wires, right? And so the voltage is described as the energy of those electrons based on the charge of those electrons, right? The charge of the electron is a known value. We're not going to worry about what it is, but it is a known number that is negative because electrons are negative, right? So what that means is that if I take this right here and I put it in right here, right, I can say therefore P is equal to I times W divided by Q. But the question for you is something that I did not give you at the opening of this unit, right? Because I wanted to ask you this question right at this moment, is, but what is I? What is current? The unit of current, right?
Is that the extra
amps.
credit question?
But what is it? No, that is not the extra
How
credit question.
fast the
It's amps.
is it electrons are moving through the circuit?
Exactly, very perfect. It's how fast the electrons are moving through the circuit, right? Or the charge, how fast the charge is moving through the circuit, but we now know that it's electrons. So then more importantly is how would I write that as a math formula? I is the movement of charge. How would I write the movement of charge as a math formula? So
Velocity. Velocity of Q, VQ.
yeah, that's good. That's a good guess.
Okay.
But velocity is the movement of something, right? So
Yeah,
if the
it's the
something
movement of
is q, then how would I write it as a rate?
Oh. Q over.
Over what? How do we describe rate? Think about velocity. Velocity is distance over
Time.
So movement of charge would be charge over
Time.
Exactly. Very good. The flow rate of anything is that thing divided by time.
Technically, if you have the equation, hold on, I gotta find it. V equals IR, and you just switch it around so you get I by itself, you could just use that, couldn't
Yes.
you?
Yes, you could.
'Cause
But
that's
I'm using
exactly what I
this.
did.
I'm using this as a power derivation to get to something else. So I don't want to keep introducing electricity terms. I want to think about it in terms of more fundamental
It's I equals V
physics.
over R.
Yes, agreed. Nicole.
Well, like you might be getting to this,
Uh-huh.
but when you plug it all in, don't the Q's cancel?
That's exactly the point. So I'm going to take this, and we're going to substitute into the P equation that I'm working on right here. So I'm just going to pull this up and put it at the top for organization's sake, right? So this is P equals I times W divided by Q. And then we just figured out that I is Q divided by T. So I'm going to add that in. So P is equal to Q divided by T times W divided by Q.
The Q's can cancel.
And so just like Nicole pointed out, the Q cancels,
So it's just W times T.
and so power is W
Divided by.
divided
Yeah.
by T.
Why is it divided?
Yes. Why is it divided?
Oh wait,
Because
never
it-
mind,
there's
never
no
mind.
Yeah.
Is it proportional?
Mathematically wise, they just move over. Very good, Lily. That's exactly right. But if Q divided by T is the rate at which electrons move, then what is W divided by T?
The rate.
The rate at which the work moves.
The rate
Power.
at which the work
Wait, W is
moves.
work in this, not watts.
W is work in this,
Sorry,
yes.
I
I know, I'm sorry.
Whoa.
We're talking about work, not power, not, yeah, right.
I'm so excited I was surrounded.
So if we think about it in the sense that work doesn't move, right?
Right.
So what does work generally mean in terms of
It
energy?
creates energy.
Heat.
Doesn't create,
It,
energy cannot be created or
conserves
transformed.
Transforms energy, so it's the rate at which it transforms energy.
Exactly.
Oh.
We're
The
brilliant.
rate at which we transform energy
Is that what?
is also known as
Power.
power.
Power is the rate at which we transform energy.
Yeah. Power is the rate of energy transformation. That is actually a formula I purposely did not give you when we did conservation of energy so that we could talk about it here and recycle back to conservation of energy.
Wouldn't it have made our lives so much easier?
No, I don't think it would have,
Oh,
because I'd
okay,
asked
then
you to
I'm
just do
okay
this
with
proof
it.
going the other way. So what I want you to think about is what an electrical circuit is doing. It is taking electrons and moving them into the circuit, right? The faster that happens, the more power the circuit is using, right? When the circuit uses power, what is happening? It's doing something. That's exactly right. So if I think about the most traditional way to measure light bulbs, right, is in watts. What is the difference between a 50-watt light bulb and a 100-watt light bulb?
50 watts.
The 100,
That's
that's not wrong.
Oh, I thought you were asking.
It's not wrong. It's not wrong. 50 watts. But more importantly, the 100 watt is twice as bright,
That's what he was asking.
right? Because the 100-watt light bulb is transforming the electrical energy into light twice as fast,
Oh.
right?
It dies faster.
That means it dies faster.
Nice,
So
Hayden.
you want to get 50 watts.
It
Well,
depends
unless
on
you
what
want
we're
the
trying to
brightness.
accomplish,
Oh.
right?
Yeah, if you want it to be really bright.
So if we
Then
think
you need
about
it to
this
be
in
bright
any
for a
sense
shorter
of
amount
plugging
of
things
time.
in, right? Anything that is going to use a sizable amount of current to generate a sizable amount of power is using a lot of electricity, right? Anything that is going to use less power uses less current and therefore uses less electricity and will last longer. And so there is a balance when it comes to building electrical devices, depending on whether or not we want them to be very powerful and happen all at once really quickly, or if we want them to last over a long time frame, especially when the voltage is supplied by something like a battery, where a battery has a limited amount of electrons. Because if I want to run something that's really powerful, I'll run out of electrons relatively quickly, and I have to be prepared for that. Lila.
So is the goal of companies that sell like cell phones or laptops to find the perfect balance between the two so that it's like the best for a consumer?
That is exactly right, right? Because something like a laptop, right, we want it to be powerful enough that you can do things like surf the internet, watch videos, watch HD videos, listen to music, and do computing all at the same time, but you don't want it to have to require gigantic batteries. All right, so
Such tangents.
suppose I have light bulbs. All right, so suppose I have similar batteries, one like this, connected to a circuit that I will continue to draw, and one like this connected to a different circuit that I will draw, right? First one has one resistor here, one resistor there, right, which I'll circle, which indicates that they are light bulbs, right? These are light bulbs attached to a similar battery here, V, to a similar battery here, V. Then I'm going to do what you were doing in part 2 of your lab, which was connect this one, this.
I like that better.
Yeah. What's the question?
One thing at a time. All right, So
I'm not
what
a
I've got
patient person.
is I've got 4 light bulbs, assume they are all resistance R. I've got 2 batteries, assume they are both voltage V. All the same
Wait, these are
electrical
light
components in
bulbs?
all cases, yes.
Yeah.
Resistors with circles drawn around them are light bulbs.
Or the upside down circle.
Yeah, agree. Also fine.
How can a
Upside
circle
down.
be upside down?
What?
What do you mean semicircle?
Upside down circle.
I'm really confused.
I like drawing out.
Circle could be upside down.
You know, everyone followed along with it till you said something.
I'm actually really good at drawing light bulbs now. From that lab,
It's good. You got enough practice.
but now I'm not
So,
able to draw them.
simple slash interesting question, right? Is that under these conditions, right? If the light bulbs are exactly the same and the batteries are exactly the same, these 2 circuits do not produce the same amount of light.
That is true.
Is that one?
Don't say it out loud. Don't say it out loud.
Can you repeat the question?
What I'd like you to think about, right, is which one produces more light and why,
Oh, easy.
right? You need to be able to prove why. So what I want you to do is mathematically,
Oh, mathematically.
using the formulas that we've just talked about, prove your answer. Right?
Can you
If
just
you do
not?
this for Monday, I will give you extra credit as an extra credit homework assignment.
I mean, I can leave right now.
Which one produces more light and why? Just
fun fact
think it
now.
over. After doing the lab, you should be able to answer the question without doing any math. Theoretically.
But we have to use math.
If you show the mathematical proof of why,
That's so good.
then I will give you extra